Okay, hi everyone. So here, the international GNSS community, we know what it is to deal with GNSS data, to manage data and to storage data and metadata. Don't let me start. So currently, there's no just one single software that covers the entire GNSS processing pipeline. Metadata is stored always in text files, text-like files. It is very difficult to keep updated. We also have GIS systems that are very useful, very powerful to visualize geographic data like GNSS stations, but those are static and very difficult to keep updated. And this becomes a big problem when we are managing networks with thousands of stations. So we have the solution to your prayers. We introduced this software. It is the geodetic database engine. So this software covers the entire GNSS processing pipeline, from getting all the data, the RINEX files, the raw files, storing, connecting to the FTP services, storing, and also the quality control of the metadata, and the processing of the GNSS files using PPP and Gamut, and then the post-processing of time series analysis, and also some geodynamic tools, and also has a package to realize reference frames. The best thing of the software is that it's open source. So Geode meets the best of these three worlds. It has a GIS capability to visualize all the information, and it's not static as GSS like environments. It also has a powerful database that is back using Postgres, and also has an entire geodynamic process analysis tools. For instance, also helps you to manage metadata, and it will tell you, for instance, if you have one RINEX file that is not covered by your metadata, it's going to flag that problem for you. When we take a look at the capacity framework developed by the United Nations, actually Geode covers all the levels of expertise, from basic knowledge as the yellow inner cycle to the advanced or expert knowledge. And it's a powerful tool for expert users and also for beginners. This is the architecture of the software. Basically, all the RINEX, station info, metadata, and also the USGS earthquake catalog goes into the database. With that database, we process all our RINEX files using PPP first to detect any problems that those files could have. Then we also have the gamut processing. And when we have the GNSS time series, we can perform time series analysis using extended trajectory models. And with those parameters, we can also realize reference frames, kinematic reference frames, a new paradigm in reference frames. So here you can see how you can create users with different permission levels. This is how the database looks. It is very fast, even with 10,000 stations. You have all the stations there. Those red stations are stations with problems, that have problems with the metadata. You can filter stations based on if they are continuous stations, campaign stations. There. So these are the filters that we have. You can filter stations, campaign stations, continuous stations, stations with problems, stations without, stations that are not working anymore. You can filter by country, and you can also filter by time window. And this will show you all stations that have data within that time frame that you're selecting. So the geodynamic tools that I mentioned, we have this earthquake database. You can select all earthquakes bigger than 6, but that can be also changed if you need it. It will you can visualize the area of influence of those earthquakes, the co-seismic and post-seismic area of influence, and you can see all the stations that are affected by those earthquakes that are within the area of influence. You can see all those arrows there. Those are the jumps at every GNSS stations. Those come from the time series analysis. And you can also download all the stations that are within this area of influence, and you can download those masks too directly from the interface. So going to show here how it looks when you get into each station. For instance, this is a campaign station. It's a passive benchmark that you go and remeasure every year or when you have the chance. You can upload all the information, the routes to get to the station, all the pictures that you take when on-site pictures. You can also upload the raw files here. You can upload the log sheets, everything from your campaigns directly here. And you can create reports for every visit, and it will create a PDF file with all the information for every campaign. Now, metadata and time series for continuous GNSS stations. Stations are measuring 24/7. We go to the station. Again, you have the routes to get to the station, pictures, all the information about the infrastructure. You have all the information about the contacts to get to the station, or the people actually taking care of the station. You have the time series there, and this green table that you see there are the parameters that are fitted to the time series. You can see the information of each one of those parameters, and that can be also changed real time. You can add parameters, you can remove parameters, you can change those parameters in real time, and it will produce the time series directly there. You can also download the time series. This is the example. You get all the information of the station on top, some of the parameters, the velocities, the seasonal components fitted to the time series. You get the jumps and the post-seismic relaxations fitted to the time series too. So conclusions. Geode manages the GNSS data analysis since the beginning of the data storage until the end. There's a Python package associated with this, so you can use the web interface to actually manage the database, or you can use directly the command line. This allows processing with Gamut and PPP, also using clustering approaches. And the results can be also viewed using the web interface. This is freely available, so please, this is the QR code to the GitHub site. And this is an ongoing project too. We're adding new modules to Geode. We're going to implement M pages to process GNSS data. We are going to expand the geophysical tools that we have. We are also adding trajectory prediction modeling of insert data. This can also be expanded for gravity data too. And we are using AI integrations for metadata analysis, for instance, to flag problems with the metadata too. This is Ohio State's team. The PI of this project is Damian Gomez. There's also Mike Beavis, Eric Kendrick, myself, Franco Sobrero, Kevin Wang, Bennett Kelmeyer, and Betsy Loaiza. And we also want to thank to the institutions that funded this project: NSF, NOAA, and the government of Canada. Thank you.